Okay, so for problem number 1, typical battery problem, okay, but it's going to involve precipitation so that it relates to this theme. Okay. So write the equation for the half reaction that occurs at the anode. So first off, they tell you that electrons flow through the switch from the PB to X. So we know that PB must be the anode, that's where oxidation happens. So that means that the reaction is going to be PB going to PB2 plus, losing 2 electrons. The value of the standard cell potential, okay, the whole E cell for this, is 0.47. And I want you to determine the value for this one right here. Okay, so I'm going to draw out the equation that you would use for this. You would say E cell equals the negative of whatever happens at the anode plus the cathode. So you're going to put in 0.47 here. You're going to get the value for the PB half reaction here and put it in here. And then you're going to solve for this value. Okay? And when you solve for that value, it ends up being 0.34 volts. And you look on the chart, and that would be the reaction for the reduction of copper 2 plus to copper solid. So that means that this is copper. And I know that I'm talking about the 2 plus half reaction because I see that going on right here. Cu2 plus. Describe what happens to the mass of the electrode as the cell operates. So we know that the mass of the cathode increases, and we know that the mass of the anode decreases. Okay, now in the text solution, I give you a more detailed answer as to why that is. So you can go down here and read that. But essentially what's going on is the metal at the anode is being oxidized and dropping Pb2 plus ions into solution. That means you're losing metal here, whereas on the cathode side, this metal here is being reduced and plated out here onto the electrodes. You're gaining mass. Okay, so let's go through each of these. I'm just going to speak the answers to these. If you lose contact with the salt bridge, the voltage is going to go to 0. Okay, the current cannot flow. If you form a precipitate in the anode, so it's saying that you're going to make some PbSO4 here, that's going to essentially pull Pb out of the solution. You're going to decrease the concentration of the anode, and that's typical of a non-rechargeable battery. So voltage is going to increase initially. And that's because the concentration of the anode is less relative to the cathode. And over time, it's just going to be less than here. So the voltage of a battery goes down, and that's simply because you're constantly losing anode and gaining cathode metal. And over time, eventually the voltage is going to go to 0. All right. So let's look at this problem. You're going to figure, so this is your water treatment problem, typical thing. So you're going to figure out, you're going to analyze the amount of silver by creating the silver precipitate. And it starts off with this concentrated HNO3. So not necessarily that related to what we're doing. So stuff like this here is not on the quiz, but it's important that you know it. Okay. So calculate the volume in milliliters of 16 molar HNO3 that the student should use for preparing 50 milliliters of 6. So you're going to use M1, V1, M2, V2, and that's going to end up being 19 mils. So you need 19 mils of that HNO3. Okay, and if you fill it up to 50 mils, you'll then have 6 molar. So it's a dilution. The steps needed for this, so it's an acid. You want to put on gloves and goggles. I would say use one of these graduated cylinders here to get 19 mils of HNO3. Okay, and then I would add 31 mils of water to the beaker that you want it to go into, and then add the 19 mils of HNO3 to that, stir, and you're going to end up with a 50 mil solution that now has a molarity of 6. You can look down below again, and I walk you through exactly how to do that. Again, the main thing here is don't add the water to the acid. You always want to add the acid to the water. reaction between acid and water is highly exothermic. So you want that to be in a lot of water, so all that hydrogen bonding can absorb that heat that's released. Okay. Explain why it's not necessary to use a volumetric flask calibrated to 2 decimal places here. So if you look at this, it's 16 molar. They're asking us to prepare 50 milliliters of 6 molar. So the precision of these graduated cylinders, plus or minus 10 mils, that's fine, because we're only looking at measuring 56. We're not looking to get more specific than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. We're not looking to get that specific. So the graduated cylinders here add appropriate precision. If you spill some of that HNO3, we're not going to add water, because that's just going to spread the acid. That's bad. And we're not going to add NaCl, because that's going to make HCl be a double replacement. We're going to add this NaHCO3. That carbonate ion right here is going to react to produce H2O and CO2. We know that from acid-base reactions. So it's a Bronsted base that's going to react with the hydrogen ions to produce water and CO2, and that's going to neutralize the acid by making water and dissolve away any remaining things as gases, decreasing the overall mass present. When I had that horrible acid spill outside a while ago, that's what I did. I added a bunch of baking soda at the end to get rid of it. Okay, so calculate the number of moles of AgCl precipitated. So here's your filter paper, right? Remember, when you do this reaction up here, you're going to make all this AgCl right here, and you're going to have floating around up here all the NO3 minus ions and all that kind of stuff, and you're adding excess NaCl. So you might have some excess NaCl here, but we're looking for the Ag, and that's fine. Okay, so you're going to filter all this through. Here's the mass of the filter paper, and they weight it to constant mass. So if you subtract those two values here and then convert it to moles of AgCl, you should be left with 3.759 times 10 to the minus 3 moles of AgCl. Okay. And then they want the mass of the silver. So some stoic, the moles of the AgCl you have here, there's 1 mole of AgCl per every 1 mole of Ag, and then for every 1 mole of Ag, whatever grams of Ag you have on the periodic table, okay? And that's going to give you the grams of Ag, and then just divide that by the grams of the entire silver alloy, which is 0.6489. By the way, this is going to be a substitutional alloy, not an interstitial alloy, because the mass of copper and silver is not that great. It's not that different. And also remember that this is going to increase the hardness of that metal, decrease the mobility of the atoms. Multiply this by 100, and you'll be left with 62.49% Ag in the silver alloy. Okay. Another problem we got going on here, similar to last time, I'll put the answers here, another water treatment problem. You got 2.59 grams of a mixture, and you're going to add these two to determine the mass of MgCl2 in the mixture. The student uses excess AgNO3. So again, we're going to precipitate out the AgNO3. Briefly describe the steps. So mix these two, mix the MgCl2 and the AgNO3, adding excess AgNO3, okay? And then you're going to filter out the AgCl, okay? And then you're just going to dry it, okay, on filter paper. Number of moles of MgCl2. Okay. So the student determines that the mass of AgCl precipitate is 5.48. So they gave you a lot of data here. 5.48 grams of AgCl. Okay. So what we're going to do here, determine the moles of MgCl2 in the initial mixture. Okay. So moles of AgCl, or grams of AgCl, moles of AgCl. And we want to back up here. We want to say that for every 1 mole of AgCl, we have 1 mole of Cl minus. Okay? And then we can say that there are 2 moles of Cl minus for every 1 mole of MgCl2. And this answer is going to give us I, which is moles of MgCl2. And then we can go down here and we can say in every 1 mole of MgCl2, you have a certain amount of grams of MgCl2. And that answer, and this is going to be 0.019 moles of MgCl2, and then this is going to be 1.82 grams of MgCl2. Okay, so you get the molar mass there. So again, it's this water treatment idea that we're adding something that's going to precipitate out the solid. Once we get that, then we can work this ratio here. By converting to moles of AgCl, we can get at the moles of Cl. Okay? And when we're at the moles of Cl, then we can understand that there's a 2-to-1 ratio between Cl's and MgCl2s. Okay? And that gets us back to the MgCl2s, and we can go from there. Okay, so this is just like the lab we did. We saw that what we were adding, we were doing this reaction, and not only were we adding liquid water, creating liquid water, but we were making this BaSO4 precipitate there. Okay, and in this case, the conductivity is really decreasing because not only are we losing ions by making water, we're losing ions by making BaSO4. This is the point in which you have no limiting reactant, okay, and no excess. If we were to look at this on a titration curve, and we were to graph pH, and remember, we're adding H2SO4 here, so it's a strong acid titration. This point here would also be 30 mils. Okay? That would also be 30 mils because this is the equivalence point here, and this is the point when we start producing excess. So what we got is we got H2SO4 being titrated into BaOH2. The first thing we got, let's write out this reaction. We have H2SO4 aqueous plus BaOH2 aqueous. And they tell us the KSP of BaSO4 is 1.0 times 10 to the minus 2. So we really know here that we're going to be making 2 precipitates, okay? Or 2 things are going to drive this reaction. The first is the formation of water, but we know that the BaSO4 is not going to be left in ion form because the KSP is so low. So the neutralization reaction is going to happen when the hydrogen ions collide into the hydroxide ions and we make liquid water. And the precipitation reaction is going to, so here's the neutralization reaction, here's the precipitation reaction. That's going to happen when the Ba ions collide into the sulfate ions, and because of this low precipitate, or the low KSP, we're going to make BaSO4 solid. The conductivity decreases here because we're losing H plus, OH minus, Ba2 plus, and SO4 2 minus. All of these ions are going away, and that's why the conductivity decreases over time. So identify the chemical species that enable the solution to conduct electricity. Well, before neutralization and precipitation occurs, we have Ba2 plus, we have OH minus, we have H plus, and we have SO4 2 minus. This is a strong acid. Remember, they're highly conductive. On the basis of what we wrote, the conductivity decreases because A, we're making liquid water, and B, we're making barium sulfate. They're not in their ion form, so the electrons cannot penetrate that solution. But as a side note, the conductivity goes back up because at this point now, we're adding excess H2SO4, so none of that is precipitating out. And we're getting something that looks like that. Okay, the more we add, the greater the conductivity. Calculate the molarity of the original BaOH2, so M1V1 equals M2V2, M1 25 mils of BaOH2, M2V2 sulfuric acid is 0.1. And the perfect molarity is that at the equivalence point. So if they gave us a titration curve, we could go down there, but they didn't. They gave us a conductivity curve or conductivity graph. So we know that that point is 30 mils. And that would lead M1, in this case, to be 0.12